Welcome this afternoon for this talk. I will talk mostly about different forms of dynamics and adaptivity for network models, and what you also can see reflected in the title. We use a type of network where we have a specification in terms of connectivity, aggregation, and timing. I will come to that in a few more details later. And we call it temporal causal networks. And then we can look at dynamics within a given network. So then you have behavior of the nodes of the network, while the network structure stays the same. But you can also look at networks that change themselves. And usually then it becomes a bit more complicated because you need kind of algorithms how you do change the network. So then you extend beyond the network context. But the notion of self-modeling networks gives a solution for that you can still stay in a network context by modeling different forms of adaptation. So then you can also have higher orders of adaptation using higher order self-models. Even the last example I will give is fourth order adaptation, as has been found in evolution. So my perspective is from the wider perspective of network science, what is a form of multidisciplinary field with different domains, different application domains. So my models usually address certain application domains, and they do not do optimization, like for example, learning, deep learning, or artificial neural network too. That's not really my area, but I try to find things in the real world and in the domains that describe the real world, and then see how they can be modeled well by networks. So this is the basic notion of network, the temporal causal network. So usually people think of a network, how do you specify a network? By the nodes and the connections. Well, of course, that's not true, and many of you know that it's not true, because even if you specify an artificial neural network, you need more than only the nodes and the connections. But still, in the wider literature, there is a kind of misunderstanding or under-understanding that connectivity is the main thing. But of course, there are other things. How do you do with multiple connections to one node? So you need forms of aggregation in your network. And that's closely related to what is sometimes called an activation function. And also you can consider the timing of your nodes in the network, because there is not any reason to assume that all network nodes behave in a synchronous way, that they have the same timing. So they are just modeling different things in the world, so they may need different timing as well. So therefore, our networks have three major types of characteristics: connectivity, aggregation, and timing, and together they specify the network. So these are the characteristics then of such a network. So the connection weights, combination functions, and speed factors. Combination functions are just a parameter then of the network, like these numbers are also parameters. So that you can fill it later after you designed the network, you still can change it into different functions, and we have a library for the functions for that. So the network structure is defined by these characteristics, but it has a definition of a dynamic behavior, which is standard in the following way. According to this standard differential equation. So you see that you look at the difference between the current state value and what comes in, and then you take fraction of that to change your current state. It's a kind of natural way of doing, or a differential equation, which is similar. So the combination function library has at the moment like 40 functions, and the well-known functions are also in it, like these functions that are often used for fuzzy modeling, these functions that are in the social network area often used, these functions, the Euclidean functions that are often used for error functions, for example, especially for NS2, And these functions, they are also very well known as being used for neural networks often. The logistic functions. So they all are in our library, and there are also these are rather general purpose functions, but you can also have more specific purpose functions. Later on, I will show a function in the library that can be used for Hebbian learning, for example. So first, I will address dynamics within the network. So the network now, the structure is constant. So all these parameters, the characteristics that I mentioned, they are now constant. And we look at the states of the nodes. The nodes all have state values at every point in time, and those state values, they change all the time. So then you can ask the general question, how does the network behavior as it emerges, how does that depend on the network structure? Of course, it depends on the network structure. If you make a different structure, it will give a different behavior in general. And one of the challenges is often, how can you relate that to each other? So the structure of the network is described by these characteristics that we just discussed. And then the challenge is to find out how properties of these characteristics imply certain characteristics or certain types of emerging behavior. So that's what I will address first. And after that, I will address the adaptive networks. So especially often for behavior, you are interested whether there will be achieved some equilibria. For example, will the values eventually converge to a common value? Like if you have a social network that models opinions of everybody, will the opinion come to one opinion in total? Will there be a joint opinion out of it or not? That can depend on the network structure, of course. And I will look at that also in the context of what you call nowadays influencers. Usually influencers play a very important role in where these values go. And then under which conditions will this happen? So that's how does that depend on the structure? That will be briefly discussed first. And the things that you can think of are social connotation of, for example, like I mentioned, opinions, but also of emotion or information, gossip, many, or even viruses like we have now. So we can relate it to stationary points or equilibrium states, or else maybe to limit cycles or even some type of chaotic behavior. That's the types of behavior. So let's look at a simple example. This is from the biological world. We have a flock of sheep here, as you can see. And will they all go in the same direction? Well, it all depends on the connectivity of the network, of course, but how exactly? So this one apparently is a kind of influencer. Let's call this influencer Boris. So all the sheep, they have their own existential questions, and so they really like to follow this influencer. So like to be or not to be, and then the influencer can tell them whether it will be to be or it will be not to be. But this example, you can also translate it easily in the human world. So that's of course, networks are a very universal types of modeling format. So you can use it for many different things. So let's consider the real world, and then we have the question to Brexit or not to Brexit. And that was a real question for the UK and still is probably. And then we have also an influencer called Boris here, and he has played a role to come to a certain direction for the people. So that's another example. With all have relate to a certain network structure. This is a different flock of sheep. It should move, and let me see. It does not move this time. Yeah. So this is also a flock of sheep. They have a different network. So this is not the type of network with one influencer, but there is just a cyclic structure. And this is just a cyclic network, and the behavior what comes out seems to be a kind of limit cycle behavior. So that's also possible to model that like a network, a different form of network. And this is still another one. We see here there are, in fact, two influencers. So then the question is, will it be one or two flocks of sheep, or will it even be not any flock anymore because there is dividedness for all individuals? It's also possible. So that's another question, whether what will happen now. So let's study this in a simulation context. So we consider this fully connected social network for now, like you can think of opinions that influence each other. And I have three different simulations here of the same network, but with slightly different characteristics. You see that indeed there are different behaviors, three different behaviors. One, there is a common value finally, an equilibrium with a common value, and here there are still equilibrium values, but they are not the same, and also here. If you look well here, there are two constant states here. That's also useful to keep in mind. So this is the logistic sum function, combination function. This is a scaled sum function, and this is also a scaled sum function used. But here we have two constant states. These states were made constant. So that makes a different connectivity in that sense. So let's see what you can say about the explanation how these things are so different. Well, there is, I have a book out since early this year, a 2020 book about adaptive networks. And in that book, I have a number of theorems, like about 20 theorems of different situations where you can do certain type of prediction of how the behavior will be. And this is one of the most basic ones. This is even maybe also known for other situations. So these theorems all have the same structure. If certain conditions on the network characteristics, on the structure of the network, and they can involve connectivity, they can involve aggregation or even timing, then and there is a conclusion about the behavior. In this case, the behavior will end up in the same value, a common value. And what are the conditions here? This condition says that every state should be reachable from every other state, except at most one. There can be one exception. And the example that I've shown, then we really have every state is reachable for every other state. And the aggregation conditions, they are a condition on the combination functions. Remember that I used different combination functions. I used a logistic on the one hand, and I used a scaled sum on the other hand. And these are three conditions in the theorem that should be satisfied in order to have this same value. And they should be normalized, strictly monotonically increasing, and scalar free. Well, the strictly monotonically increasing, you can imagine what that property means, that the values become higher if the input is higher. That both functions, they have that. So that's not a problem. But scalar free, not. Scalar free, that property means that that's half of the definition of linear. But the definition of linear has two things, the scalar part and the sum part. If you drop the sum part and only take the scalar part, that's what I call scalar free here. And of course, the scaled sum has that property, but not the logistic function. So that gives us the possibility to understand from this analysis why these behaviors are different. So this is strictly monotonic, but it's not scalar free. So therefore, there is no joint outcome here. They are strictly monotonic and scalar free. So then all values are becoming one in the end. So that explains this. And this one is still a bit different because we still have this function that satisfies this the type of conditions on the aggregation, but this one does not satisfy the connectivity condition because you remember that I told that there's possible of one exception that is not reachable from other states, but we have two states that are not reachable from other states, these two. So that's too much, too many. So therefore, in this case, it's not the reachability or the correct condition on the connections is not, and the connectivity is not fulfilled. So therefore, in this one, there is no common value. So that's just an example how you can analyze the behavior of the outcomes of emerging behavior based on the network structure. And in this case, you see that it's a combination of the network structure concerning the connectivity, but also a network structure concerning the aggregation form. So therefore, in this case, for example, with theorems like that, there are also theorems for tree-like structures, acyclic graphs, networks. So then by such theorems, you can just predict that in certain circumstances, there will be one value out of it. So for example, in this case, will this be one flock of sheep or will this be two? Yeah, you have, as I indicate here, we have two influencers, so there's still the possibility that it becomes two flocks or that everything becomes divided like in the simulation cases. But fortunately, in this case, we have a kind of super influencer, and therefore this job is very important of the person to keep one flock. So therefore, that's the reason of existence of that type of job, that he can keep it as one flock. So that's the big super influencer then. Okay, so that's for the normal networks they have their own internal dynamics and they are not adaptive, but let's now consider the idea of adaptive networks. So the main notion I want to discuss here is the notion of a self-modeling network. And well, of course, how can a network model itself? Yeah, it's not you should not read it like, oh, I have a network and I don't need to do the modeling anymore because the network does it. No, it's not like that. That's asked too much. And by the way, you need your job, so then you would lose your job even. So you still need to do the modeling, but the network will help you. You can just add a self-model to your, say, base network. You start with a base network, you add a self-model to it. And what's that? That is a subnetwork where there are additional states that represent network structure characteristics. Let me explain it in a bit more detail. So you can have connectivity characteristics, you can have states to model that, to represent that. You can have aggregation characteristics, you can have states to represent that, and you can have timing characteristics like the speed factors, and you can have states to represent that. So, for example, there is some adaptive connection weight, then you add a state W to your network. Or you have a combination function parameter tau, like an excitability threshold, and you add a state T for that. And you have a speed factor, and you add a state H for that. So then you have a number of states that are the states for the self-model. Of course, the self-model also needs connections and all the other characteristics, so you still have to add that too. You should also keep that in mind. But these are the states, at least. I will give some more detailed examples shortly. So let's consider first the idea of plasticity. That's a very well-known idea, for example, in neuroscience and cognitive neuroscience, that the brain structures, they change, for example, by Hebbian learning of connections. This is a form of what you can call first-order adaptation. Later I will explain how you can also have other orders of adaptation and how they look like. So then in some network model, you have some of these characteristics are adaptive, and you can handle for a self-model for these adaptive characteristics. For example, if you want to model Hebbian learning, I already said you can add such a state W. You need some incoming connections for the states, and you also need some outgoing connections for the state, and you need also the combination function for the aggregation in this state. Well, the combination function is a very easy declarative description. So that's a side remark. The whole approach that I'm using is a declarative modeling approach. Even if there is very dynamic and adaptive types of behavior involved, the means to specify it are just declarative mathematical relations and functions. And this is an example. What you often see if people describe learning approaches or methods, they always use algorithms or procedural things or even program code to describe them. Well, that's a pity, because you can also do it in a more declarative way. Then it becomes easier to have mathematical analysis as well for the behavior that comes out. So this is the V1 and V2 are the activation levels of the connected states. The W is the connection weight, and that's there. And the mu is the persistence factor. If this persistence is 1, then it's fully persistent. If it's 0, there is not any persistence. And if it's like 0.9, then you lose 10% of what you have learned every time unit. So you should read it like that. So this is part of the specification of the characteristics of this W. So this is the aggregation characteristic for this W. So this is just another function often used from the library. There are also functions for social networks like bonding by homophily, where you also have different formula, but still a formula like for these types of variables. So there are many of those functions as well in the library. So except the synaptic plasticity, what's also often used in artificial networks, there is also possible non-synaptic plasticity. This is a quote from Chandra and Barkay, and they point out that, yeah, there is also, of course, plasticity of the synapses, but there is also plasticity of the intrinsic neuronal properties, like the intrinsic excitability. And they also play an important role in the learning related to behavior, for example. So therefore, also in networks, you want to consider more than only the connections if you want to consider adaptive networks. So that's a thing that will also be included in the example that will come soon. But before I do the example, I want to discuss now the step also for second order adaptation, or like it is called in the literature of cognitive neuroscience, metaplasticity. So the question is, when and at what time and when, under what circumstances should the brain have plasticity? It would be not good if the brain would be plastic all the time. So there should be moments that it should be plastic, and there should be moments that it should not be plastic. So from viewpoint of the functioning in the real world, it would be quite a kind of not so very flexible solution if there's always the same plasticity. Well, they found out in neuroscience that indeed that's not really the case. The plasticity is changing all the time. So therefore you need some forms, you can call it control of plasticity. You need some forms of handling that. Well, that's called in the literature then metaplasticity, and for adaptation you can say it is second order adaptation, because what you do is you adapt the first order adaptation. You make adaptations on the learning, for example, and learning itself is first order adaptation, and therefore the adaptation type is second order. So these are two things from neuroscience literature. Adaptation accelerates with increasing stimulus exposure. So stimulus exposure is one of the factors that influence your adaptation speed. Say your learning rate. That's what is meant here actually. But also other things, stress levels. Stress is not very healthy. And one of the effects of stress level is that they slow down or block even adaptation. There are many stress-related disorders, even mental, but also physical disorders. And then people get locked in a certain situation because they cannot change themselves anymore, because they have locked the metaplasticity. They have no possibility to adapt anymore. So that's also one of the things that have been found out in, say, the last 10, 20 years, more and more. So that's also how we do. And note as a side note that the self models, so we now will also make second order self models, but for both types of self models, they are just also available in the physical world. They are not like fantasy or constructs. In modeling, you may make constructs like intermediate steps in your calculation where these intermediate variables do not really have a meaning in the world. But here in this case, all these self models, they have some physical, say, realization or embodiment, or how you should call it. So the synapse, of course, the configuration of the synapse, that's what determines the weight of the connection. But also the internal neuron configuration, they define what the excitability is of the neuron. And for example, considering the stress, like things like cortisol levels, maybe, they also define the metaplasticity. So all these self models, they have their own real counterparts, you can say. But this is a side remark. I will not go on this. I have other things, other papers where I will address that a bit further, but not this one. So using such a self model in two levels in this case, for plasticity and metaplasticity, I will show a simple example. This is the example from my book that I mentioned, chapter 4. So we have a base network. This is a simple base network. This is a sensor state for some stimulus S. And the stimulus S has some sensory representation in your brain. There is a belief state. You interpret the stimulus in a certain way by some belief state. And this is a preparation that you want to do maybe as a response to this stimulus. We focus here on the connection from the representation of the stimulus to the response preparation, and also to the excitabilities of these two connected states. That's what we are doing now. So therefore, we want to have a first order self model here. And we make a state for this connection. This state just represents the connection weights here. And these states, they represent the excitability thresholds here. Keep in mind that logistic functions, they just have a threshold parameter. So it's very simple to use that one to model this type of excitabilities. So these pink arrows, they define that these values are actually used in these base level states as the characteristics that you want to do for them. So this arrow defines that this value from this state is used here as the threshold value in your logistic function. And this here, this specifies that in this state, when you make the update function here, then you use this value as your connection weight. So that's how these downward links, so the downward links, sometimes I call them, they define the special effect. So that's the special effect of these different types of states. So we have now a self model, a first order self model with these three states. So part of it is a connectivity self model and part is aggregation self model. So one is for the synaptic plasticity and the other one is not synaptic plasticity. But that's not the end of the story, because we already talked about metaplasticity as well, and it's even in the title still. So let's also look at that. Of course, there are also upward connections needed. For example, the W connection, the one that should do the Debian learning, needs input from the activations of the two connected states. So therefore, these blue arrows are giving that input, because you want to learn depending on the activation, the say simultaneous activation of your connected states here. So that's why there are two here. Well, and for the excitability threshold states, they also have some information from different sites, even in this case. So let's look then at the second order self model. So given the literature I already briefly mentioned, we can consider the speed of the learning as something that we can control. Yeah, we will do that indeed. So we'll have a vector, a state h of this w that represents the speed of this the learning rate here, say the speed of this state, because the speed of that state is just the learning rate. So that represents that one. This one is a different one. This defines the mu factor in the Hebbian learning, the persistence factor. So this state, if it's 1, it's fully persistent, and if it's less than 1, it's not fully persistent. So then the special effects, they are incorporated here also by these pink arrows. So that's now we have these states. So the A state does the time is a timing self model for a first order self model state, this one. And these are aggregation self model states for the persistence mu of this one as well. So that's how you model. Now we need also the upward arrows here. So let's add the upward arrows, so also the upward arrows that gives them the right input. And also these states need their own combination functions. In this case, they have just the logistic function as well, because sometimes you can also use the logistic functions for self-models. And that's not the case for Hebbian learning, because that's a rather specific type of form that you want. So therefore they have their own special purpose functions, but this can be just based on the standard functions. So that's the model then that we have. So we have these different self-model states, and this is just a summary of them. And there are first order self-model that's there, and then there is a second order self-model that's there. So the question, what is a self-modeling network? This is an example of a self-modeling network. It models itself. You see that this part models this, this part models this structure, and this part models this structure. So that's how it models itself. You can say, yeah, but this part is not modeled by anything. Yeah, of course, if you still want to model that, then you can have another plane on top of it. And if you want to still model that, you can go on infinitely. But anyway, in most cases, you are already happy when you can model some of the levels of your model, and you don't need to model the highest level anymore. But it's even possible to have a cyclic structure that the levels finally come back to the basic levels. So maybe some of you know the book of Hofstadter, who wrote a very thick book called Keudel Escher-Bach about it. And we also have 1 or 2 papers about that actually. It's in chapter 8 of the book as well. But anyway, for now we are satisfied that only this part is not part of a self-model. These things are already in some self-models. Okay, well, the simulations then of this example model, these are the base states plus the connection weight. You see here that the learning curve of this W of this connection weight is not what you normally see. Normally you see a slightly different shape. It's here more steep and straight than what you normally expect from learning curves. But that has a reason, because there is controlled learning here. So I will show it in a minute. So this stays here. The persistence is the mu, the persistence value initially is 1. So it's fully persistent here, and there is no learning here yet because everything is low. There are low activations, so there is no learning. So therefore this is practically constant. It stays at the same level. But then we have this control. And that's the other picture. These are the other states in the model, the higher levels. This is still the same W curve. You see here the learning rate, the speed. And indeed, it's very close to 0, and even here it's almost 0, or maybe it is practically 0. But then at some time it becomes higher because of the stimulus exposure. You remember the criterion of stimulus exposure that accelerates the adaptation. And that is modeled in this case. So therefore this goes higher. And therefore here, now there is learning possible. And there is still another, this is one boost. This a boost in the learning rate. But in the model there is still another boost, excitability, because also the excitability was dynamic. also adaptive. So they are high in the beginning, but they become very low, even below 0.2, which is very low for an excitability threshold. So therefore it gives a boost on the activation of the states, and that also gives the boost to the learning itself. There's also a slight change in the persistence here, but that doesn't make a lot of difference. You see that it's low. That means that you lose learning results, the level of learned rates. So therefore, you could have even have had a drop of this red curve, but the learning is so fast already that compensates for it. So this does not actually make a difference. So therefore, finally, the learning will take place, and later it will still come high again, the persistence. So this is one example. I hope that this has made clear what I do with these self-modeling networks and how they can be helpful in give a kind of, say, transparent idea how to handle learning and how to handle control of learning in a very, what I think, very transparent, declarative manner. So I didn't I didn't show you any algorithm description or any procedural description or any program code. They're just a choice of functions from the library that can do this. So that's the part on adaptivity, and even adaptivity of 2 levels. As the next step, I want to go to higher order than the 2. So I was when I was preparing the book, I was thinking how many levels of adaptivity can I find in the literature. It's not easy. There are second order is, you can find some of that, but third or higher order is difficult to find in literature. Well, I found something in the biological literature on evolutionary processes. So this idea is that we have, I think I missed this one. So this is some fragment of a paper of Fessler et al. And they describe that there are some things, it's called disgust, what is happening during pregnancy, that you can consider that as a third order adaptation. And then the pregnancy itself, you can consider it as a second order adaptation. I adopted that example and I worked it out in a model, but I also took into account the adaptation that introduced the pathogens, like the viruses and all the bacteria that makes us ill, like even in these days. So the general idea is that there is for your well-functioning of your body, you need some causal pathways that makes that the food gets in the right places in your body and also the oxygen and everything. So they are the things that give you a good health. But then after a first order adaptation in the environment, pathogens occurred during some states of the history. They have causal pathways that have an important, I wouldn't say intention, but at least they have an important effect, that they negatively affect your healthy pathways, that without them, give you a good health. So these pathways that you already have, they are disturbed by new causal pathways of these pathogens, say viruses or so. So then, of course, we know, and there is a lot of discussion about that nowadays, we have an immune system to protect us against such pathogens. Well, that has also been developed during the evolutionary history. So I'm just talking after the biology people. So this is not my own achievement that I know this, but they describe it like that. So then as a reaction of these pathogens that occurred, then there is the immune system, and the immune system has its own causal pathways to disturb the causal pathways of the pathogens. So that's in a sense also controlling those causal pathways again. But then there are still more. We have third order adaptation. At some time, evolution found it a good idea to make people pregnant, at least half of the population. and so that we can mix different genes for different persons. But that has that introduces a real problem, because to get pregnant, you need to accept that you get deep in your body foreign material from somebody else. Normally, an immune system would just kill that. So you would never have a pregnancy if your normal immune system would kill everything that comes in. So therefore, it has a third order adaptation. During the first 3 months of pregnancy, the defense systems, your immune system, becomes less strong. It becomes suppressed in a certain way. So, but then you have the risk to become ill. So then you are also vulnerable for other things that come from outside. So therefore, evolution invented the idea of disgust, so that many things you find disgusting when you're pregnant in the first 3 months. So you avoid many things that are not very normal in the sense that not so they may have risks in them. So that's according again to this biologists, is that the disgust was there because you had to do something about this problem of the lower active immune system because of the pregnancy. So that's another way of adapting your immune system. Then in this case, it adds another type of defense, namely to avoid some people call that in the biology, it's called behavioral immune system. So then the general idea is that evolutionary adaptation usually concerns affecting existing causal pathways. So you already have things that were created in the past, and new steps in evolution add extra causal pathways that regulate in a certain way the existing causal pathway. I would not claim that it's always the case, but at least it happens in quite a number of cases. So this makes that levels of adaptations are created in the real world again. So they are not fantasy, but they are really there in the real world, where causal pathways at one level are adapted by causal pathways at the next level. And that's also what I will do here. I will illustrate it by a relatively simple model. And that's a 4-level self model. So it's 4th order adaptive. Each level includes a self-model of a causal pathway as developed in the lower levels, and by a downward connection, each level's causal pathways affects that causal pathway below, and that is described for this case study. So remember that we had the first order adaptation is that pathogens develop, second order is the immune system develops, the third order is pregnancy is supported, and the 4th order is disgust develops. So this is the base level. So to make it to keep it a bit simple, the term causal pathways, I made it simple. I made just one arrow for the whole causal pathway. So it's just a bit abstract. So there should be a whole causal pathway in between these things. This is the causal pathway from the environmental context characteristics or states, and to the mental health, the health level. The E is the health level, the E1. So this is the starting point. That's before the pathogens were there. There was a happy life like this. There was an environment, and you had a good health because of the causal pathways in your body. But then the pathogens came in, and what they did, they made a situation, a causal pathway, this one, to affect your own causal pathway. And this is just a W state like we had before, not for Hebbian learning this time, but still to represent this connection of this. So that makes that this becomes lower, this value becomes lower, and therefore this pathway doesn't work so well anymore. That's what this pathogen does. Well, then this causal pathway for the pathogen, we need this immune system to affect that one. So therefore we need a state to represent the connection weight for this arrow, and that's this one. So that's what the immune system does. It has its own causal pathway, and then the pregnancy comes in, and you want to do is something with that. So then there is something, this one becomes lower, makes this weaker, this connection. And then finally we have the disgust coming in, so that makes that this whole thing repeats again and gets this structure. So that means we have four orders of self-models and fourth order adaptivity in this type of process. So there's also some simulation. These are the adaptive connections. I don't know whether we can also see this as adaptive, whether there are still further evolutions going on. I didn't see that in the literature. And that's the whole model. So of course, as I said, it's a bit simple because the whole pathways, I just shortened them to one connection. So this is one scenario. This is only the scenario when the first two adaptations happen. So you see here, there is here the happy life before the pathogens were there. So good health. The red line is the health level. But then the pathogens came in here. And then you see that immediately the health level goes down because your own causal pathways are affected in a bad way. So therefore the immune system is developed, that comes in here. And then you see again that the health level becomes a bit more acceptable again. So it comes here. So that's if you have the first two, but now we still have the idea that there should be pregnancy possible. That's the second scenario. Then we have also the pregnancy coming in. That's this one. By the way, these coming in of these things, I have just it's just an external factor for the model. I just modeled that as an external thing. It's not affected by the model itself. You could go further and try to do that, but that would be really a much more complex model probably. So this is the pregnancy is coming in, and then you see that it has a negative effect on the health again. So here you can say get a bad health because of becoming pregnant, because there is not a disgust developed yet. In the last scenario, we also have the disgust. So here we note that the time scale is longer and longer all the time. So here we have the disgust developed, and then again the health is coming up again. Yeah, it still comes up further, but it's going on only till 600. So that's the example of this. It shows how these different adaptations and different levels of control work. And it also shows how in nature it really exists. I could have called the title of my talk also something with natural computing or whatever, because I'm just doing the modeling inspired by the nature and just to model the natural things. Even in social world, you can also call that kind of natural world. So that's what I usually do for my living. So this is the second example. I've shown two examples, and I think now we can close it for now. That's the whole topic. So I discussed that network science in the broad sense as a multidisciplinary field addresses several domains. And in many of these domains, dynamics and adaptivity are important. They play an important role. We have the idea of dynamics that's implied by the network structure, and I illustrate it for the case of the dynamics within a network. But notice that after you add self-models to your network, in the extended network, the dynamics of the extended network still is implied by that network structure. So that's the idea stays the same. So then the adaptive behavior is implied by the structure of the self-modeling networks. So you still have the same situation. You have a structure defined by declarative means like functions from the library, or you can also add your own functions to the library as well if you want. But they are just mathematical structures, not procedures or algorithms. They're just mathematical structures like relations and functions. And that's what's defining the structure of your network, and the behavior is implied by that. And then you can look for certain theorems that relate that indeed. Of course, I don't say that you can explain any type of behavior, because that's not true. But also what's not true, what some people sometimes think, is that linear models, they imply understandable behavior, and nonlinear not. That's not true, because the Euclidean functions, maybe you remember them with the nth power, they are not linear. They are scalar free, but they are not linear. And they still follow the properties of the theorems very well. So the theorems, most of the theorems also work for them. So the borderline is not between linear or nonlinear. The borderline is between types of functions that you can think of good handling of them or not. So higher order adaptation can be modeled by multi-level self-models. And you can have a lot of interesting applications in your book. In my book, you can find some of them. There are also more papers on my ResearchGate site, for example. And you don't need programming, because the modeling is purely based on mathematical functions and relations, and we have a dedicated software environment for that. So you can see the references in the paper itself. There are more references, but here you see this is where you can find the software. You can download it. This is the where you can find some exercises to just try out. A simple, not too complicated exercise to learn to use the software. And here you can find more in general different papers. So I think this is it. So maybe you still have some questions.